So, in the series of basics of software defined radios and practical applications, we are discussing distortion parameters, and we have seen the distortion due to power amplifier nonlinearity, and now we will see the specifications which defines the impact of such distortion on the signal quality. So, this was the expression which we had seen for the amplitude of the IMD terms when this is the nth order IMD and if n is the odd number. We have discussed that the IMD3 and the odd order IMDs, they come near to the actual signal and they are more important. So, let us have a look if these IMDs have any relation with the input power. For this analysis purpose, let us assume that the amplitude of both the tones are equal. So, signal power for both the tones x1 is equal to x2 is equal to x. Now, let us say it is in dB and we want to calculate the respective voltage for this thing. We have discussed earlier that when we want to convert from watt to dB, it is 10 log 10 P, W means watt, and it becomes P in dB. If we do 10 log 10 PW, not PW, in milliwatt, then it is P dBm, and P dBm is actually your power in dB plus 30, because in milliwatt it is 10 to the power 3, so that becomes plus 30 here. So, this relation we have to keep into mind. Moreover, we have discussed earlier that whenever we are working with the RF circuit, our cables, they have to be matched, they have the impedance of 50 ohm. So, R naught is always 50 ohm, and we match our components which are to be added to that cable to this 50 ohm. So, all the power calculations happen with respect to this 50 ohm. So, basically if we want to convert a voltage to power, it will be P W will be V square upon 2 R naught, or it will be V square upon 100. So, we will keep this in mind and we will do our calculations. So, we were starting with the point that our signal power at both the tones is x dB. Now, we want it to convert into voltage. So, what will be the relation? 10 log 10 V square upon 100 should be equal to x. We can also write it 20 log 10 V upon 10 equal to x, or we can say our voltage is actually 10 to the power x upon 20 and multiplied with 10, right. So, x upon 20, 10 to the power and multiplied with this thing. So, it is for the signal, main signal, S is representing our signal voltage. Now, if this is our signal voltage, we had seen from our expression that for the second order intermodulation, it is always x1 into x2 or x1 square x2 square. Now, we have assumed that x1 and x2, they have the same power of x. So, for any of the second order distortion, it becomes x1 x square again x square. So, any kind of second order intermodulation, we can say that our voltage is becoming double. Please keep in mind, in this table, this x are representing your values in voltage, in amplitude. In my assumption, this x1 x2 I am representing power. So, please bear that in mind. Now, our IMD2 component, let us call it VIMD2. it should be square of this term Vs square. So, it will become 10 square into 10 into x upon 20 into 2, or I can say 100 into 10 to the power x upon 10. So, this is the voltage here. Now, if I want to convert it back into dB, so it is in watt, V I m d2 in dB will be what? Again 20 log 10 V I m d 2 in watt divided by 10 by using this relation again, right. So, we are getting our power in dB here. So, let us simplify this. It becomes 100 into 10 to the power x upon 10 divided by 10. It will cancel out one of the data. It will become 20 log 10, and it will be 10 to the power x upon 10 plus 1. Now, they have the same base. So, if we take it before this, it becomes 20 times x upon 10 plus 1, and this term will be log 10, 10 means 1, right. So, final expression becomes 2x plus 20. So, let us keep this in mind. Now, if signal power is increased by plus 1 dB, so x1 is x2, but now the power has been increased by 1 dB, so x plus 1 dB. So, what should be voltage corresponding to this? Again we can do the calculation like we had done the calculation here. 20 log 10 Vx upon 10 is x plus 1. So, we will have our expression like that. Instead of x, we will have x plus 1. So, new Vx will be 10 into 10 to the power x plus 1 upon 20. So, we have increased case 2. So, case 1 was when we have power x, case 2 is when we have increased power by 1 dB. Now, Vx is there. So, what will be the IMD2 component for this? V IMD 2 in what will be the square of this term. So, again 100 into 10 to the power x plus 1 upon 10. So, we have done all these calculations. Instead of x, we are using x plus 1 here, right. So, it is for the power when one power is increased by 1 dB. Now, let us calculate the power for this one. Actually, this should be power also, because we are calculating power here, right. So, P IMD 2 dB should be 20 log 10 and V IMD 2 which has been converted, we should be converted it back into our power divided by 10. So, it becomes 20 log 10 and 10 to the power okay. So, it is 100 into 10 to the power x plus 1 upon 10 here, and it will be divided by 10. So, this will go away and the expression becomes 20 log 10 10 to the power x plus 1 upon 10 plus 1, right. So, we take it further, it becomes 20 x plus 1 upon 10 plus 1, and 10 if they have the same base it will be 1. So, if we simplify it, it will be 2x plus 2 plus 20, right. So, initially when it was not increased in 1 dB, it was 2x plus 20, now it is 2x plus 2 plus 20. Okay, so what this is the impact on the second harmonic. So, if we increased our input signal power by 1 dB, the second harmonic second distortion terms which can be harmonic or the distortion terms, they increase by 2 dB. Now, let us see what will happen for the third intermodulation modulation product. So, whole calculation they have to be done for the third intermode. So, it will become cube. So, it will be cube and it will be 3. So, it will be 1000 into 3x upon 20, and again the calculation here will have the same factor. It will be 1000 into 10 to the power 3x upon 20 divided by 10. It will be cancelled out and it will become 3x upon 20 plus 2, and the output individually will become 3x divided by 20 plus 2. So, it will become 3x plus 40. So, for the third IMD product it will become 3x plus 40 dB, right. So, it is IMD 3. Similarly, if I increase our signal power by 1 dB, then I am calculating for the third intermodulation product, then what will happen, that we can take the calculation from there. It will be 1000 into 10 to the power 3x upon 20, and we can put that value here because it is third power, and instead of x we should use x plus 1 because we have increased by 1. So, now let us do this calculation for IMD 3. So, 1000 into 10 to the power 3 times x plus 1 divided by 20 divided by 10. So, this goes here. So, 20 log 10 and it becomes 10 to the power 3 x plus 1 divided by 20 plus 2, and if you simplify further, 20 times 3 x plus 1 divided by 20 plus 2, and the output becomes 3x plus 3 plus 40. So, now for the third order distortion, if you compare this term and this term, by increasing the signal power by 1 dB, we have increased the signal power IMD power for the third intermode by 3 dB. So, by increasing the signal power by 1 dB, we are getting the variation of 1 dB, 2 dB, 3 dB for the intermodulation product. For the first order it is 1 dB, for the second order increase it 2 dB, and for the third order the increase will be 3 dB. So, it represent a straight line because the variation is only incremental there, and it is shown in this way if we are plotting in the logarithmic domain. So, if we plot our input versus output, and this axis is input power in dBm, output power in dBm, then they have a linear relation with respect to each other. Because of this relation, we can have the intercept of these lines with the original signal line, and these signal points are called intercept point or IPN. So, this n is representing the order of the IMD. So, if it is second order, so it will be IP2, if it is third order, it will be IP3. So, in this diagram we are showing the diagram that for P omega 1 is the actual signal which we should receive. So, this is the original signal, and because of that the second order distortion, their power, it is being plotted here, and for the third order it is being plotted here. And if you see in this diagram, if we keep increasing the trajectory in its original path, they will intersect at some point. So, these points where they are actually intersecting with the original signal power path, they are called IPN. So, this the power of this can be calculated based on the equation of line, and this is given by the formula n times the original signal power minus n minus 1 IP n point, where it is intersecting the P omega 1 point. If we know these 2 points, these 2 values, we can calculate the IM n product. For example, for second harmonic component, for the 2 omega 1, n will be equal to 2. So, 2 P omega 1, and P omega 1 is the power of the original signals, and n is 2, so n minus 1 is 1, and IP2 value you can put there. So, by if you know these 2 values, IP2 point, and you know the P omega 1 values at that point, then you can calculate your power at 2 omega 1, that is the power of second harmonic. Similarly, for the third order intermodulation, which is very important, it is near to our signal. So, it is third order because 2 times of one frequency and 1 time of other frequency, so 2 plus 1, third intermodulation. So, n equal to 3 times P omega 1 minus n minus 1, 2 times IP, n is equal to 3. So, by knowing these 3 values, we can calculate the distortion component, and vice versa. If you are able to measure the IMD terms by some measurement instruments, and then you can define this IP3 point, that where it will intersect the path of the original signal. So, it is one of the definition which is used a lot in the communication system. Another definition is P1 dB gain compression point. So, as I told you initially that when you plot your P out versus P in, it is straight line, but after some time it becomes saturated and it becomes almost constant, right. So, the point where it is 1 dB compressed with respect to the original path, it is called 1 dB point. Means if we keep increasing, if we keep drawing this original path, the path when it deviates 1 dB with respect to the measured path, it is called 1 dB point. So, this dotted line which we are reading in the P in input power will be called 1 dB input compression point, where the data is compressed by 1 dB with respect to the original path. So, this is a very important parameter. Most of the commercial sheet, they provide you the P1 dB gain. So, you can have some idea, if this P1 dB gain is very high, you can assume that your device is quite linear for a long range. If it is low, it means it will be saturated very early. So, this is how it is provided in the commercial data sheets. Now, the rule of thumb for calculating P1 dB power based on the IMD3 power is given by the formula. For solid state power amplifier, P1 dB can be calculated by its IP3 power, third intermod intercept point, minus 10. It is a rule of thumb which has been seen by measurement. People have measured so many times for the different solid state power amplifier, and they found that normally they follow this rule. Similarly, for TWTA, the rule is IP3 minus 5. So, what do we see from here? If we have same IP3, we have intersection point which is similar, then our P1 dB point comes quite early as compared to the SSPA. So, we can say from here that our TWTA is more non-linear with respect to SSPA, because our P1 dB point is coming earlier as compared to the SSPA point. So, it is saturating earlier as compared to the SSPA point. Again, it is important to note, if we are able to have our IP3 calculation, and we have seen that IP3 calculation we can do if we know the signal power, and if we are able to measure the intermodulation power, IP3 value we can calculate easily. And once we have IP3 value, we can actually define our P1 dB point. With this P1 dB point, we can actually decide which power amplifier to purchase by looking at the data sheet of the power amplifier. Now, one of the important parameters is carrier to intermodulation ratio. So, it is defined at the ratio between the useful output power and the IMD power, which is normally given in terms of logarithmic units. So, it is in dBc. So, if in the frequency domain, these are your two tone signals at omega 1 and omega 2, and these are your IMD terms. Then this C by I ratio is carrier to intermodulation level. So, what we do? We calculate this in dB, and the difference between these power levels, this is called C by I, difference between the actual carrier signal and your intermodulation product. Normally it is third order intermod, as we discussed before. So, because it is more prominent, then we can calculate it for this case particularly. IMD3, this is the formula, 3 times the actual power minus 2 times of IP3, this is what we have calculated earlier, right. This is what we have calculated, original power minus IP 2 times of minus IP3 power. So, this is what we are writing here, this is what we can see, the output power of the signal 3 times minus 2 times IP3 at the output. So, after that we have to calculate the C by I ratio. So, carrier in this case is actually P out, right. So, it becomes C by I in dBc will be actually P out in dB minus IMD 3 component in dB. If we do that, dB or dBm, as I told earlier that dBm is nothing but anything x, dBm is nothing, it is just x dB plus 30. So, this addition term, it can be dBm or it can be dB, because it is a difference between these two parts, 30 portion will be cancelled, right, x carrier minus xi, so it will be cancelled, so it does not matter. So, P out dBm minus IMD3 in dBm, let us say. So, IMD3 in dBm we have seen 3 times So, if you solve this further, it becomes 2 times IP3 minus 2 times P out dBm, or we can take 2 out and becomes the expression which we are seeing in our PPT, right. So, the difference between IP3 out and the P out, and we take the twice, it works very fine for the C by I estimate. So, we can have some estimate by using these thumb rules. Now, the other parameter is spurious free dynamic range SFDR. We have seen this SFDR earlier in when we were discussing mixers and A to D, D to A converter. This is basically the ratio of output power with respect to the noise level or any distortion. So, this distortion which is coming from the IMD, if it is higher than the noise level, then this is called SFDR, and this SFDR will be very much equivalent to C by I in that case if this IMD is prominent. If this IMD is below the noise level, then this SFDR becomes actually peak power to the noise level. So, this is just a definition, but it appears a lot in the commercial sheets. So, this is where we are showing the range of SFDR, where our noise is prominent and our IMD is not there at that time. So, spurious free dynamic range in terms of input power will be up to this level, because after this level our IMD power starts increasing and this component will start going above the noise level. So, in the sense of input power, this will be the range where we will not see any IMD. Now, this SFDR can be computed in terms of the noise factor. If you remember our earlier lectures, we have covered this topic when the output from the chain of these components in a transmitter, or in this case receiver, it is the total gain of the system, noise figure of all the systems, input noise which is calculated as minus 174 dB. When it was the Boltzmann constant, it was our it was the Boltzmann constant, it was our temperature in Kelvin. So, with that calculation KTB, it was giving this value, and this B is actually detector bandwidth. So, we already have this calculation N out output noise power. So, if we know this thing and we calculate this convert it from watt to dBm, and we apply IP3 out dBm minus N out dBm, then the twice of this gives you your C by I ratio, this is what we have calculated here, and divide by 3 gives you SFDR in dB. So, this is the ratio they have given, but for the third order basically. So, we can use this calculation to calculate SFDR with respect to our C by I or with respect to our noise figure if it is known. Now, we have discussed till now single carrier signal and two tone signal. Now, let us move to the multi carrier or wideband signals. When we are having two tones, we have seen that we have some of the IMD components. Now, let us assume it is multi-tone, and multi-tone in a way that it is quite nearby. So many carriers in this small space, multi-carrier, multi-tone system. So, how its output will be looking like? For two-tone system, we saw that we had some IMD3 components here, 2 F1 minus F2 and 2 F2 minus F1. These were here. Now, because of other components, we will see something like that. So, this was the original range and now it become the range, and these all are the distortion component. Basically, they are IMD components, but they are so near to each other that we cannot separate them from our eyes. Okay? So, basically it will look to us like something like that, because we cannot distinguish all of these components separately. So, this is how it will look. Some signal which is our wideband signal, and then some distortion which is moving like that up to some distance. So, this is what we call wideband signals, and they behave little bit differently from the single carrier and the two tone signals. One of the concepts which we keep hearing is peak to average power ratio. This is the ratio between peak power and the average power. Because our signal is multi-carrier, so it keeps fluctuating. If we want to have example in time domain, if we see our single carrier signal, it will look like the signal is varying, but its envelope is constant. It is always going through this envelope. In two tone signal, your envelope becomes something like that. So, your signal, original signal is like this, signal is this which I am plotting here, and the envelope is varying like this. So, this kind of signal are called varying envelope signals, and with two tone it is like this, with multi-tone it becomes even more distorted. So, you will have some strange kind of envelope, you can have anything because they are more and this is how the waveform moves. So, basically when you calculate the average, the average can lie somewhere here of all the values, but the peak can reach to some higher values. So, because of that this PAPR comes into picture, which is the ratio of the peak and the average power. And how it matters? Suppose this is your input power in dBm and it is your output power in dBm, and this is your power amplifier, how it looks like, right. So, it was linear till here and after that it becomes starting getting saturated. So, I want to drive this amplifier here so that it is not that much distorted. If my average power lies here, then my signal average power is here, but because peak is going to other values here. So, peak the signal when we are applying this, it is not constant and some of the peaks can even go here. So, in those cases some of the IMD components will be generated very easily. So, what I have to do? I have to back off it by PAPR of the signal. It means the peak value from the average, whatever is the distance, I drive my PA here, which is the PAPR of the signal. So, my signal power is average power is here, but some of the signal amplitudes they reach till here. So, peak is falling here, but average is here, and all the efficiency calculation and everything they happen with respect to the average power. So, this is the power which will define all those components, means output power will be coming from here, and although sometimes it will go higher, but mostly it will remain here. Your efficiency will be calculated with respect to this point. So, this PAPR is very important factor for this case. So, we are stopping the lecture here, and tomorrow we will continue with this kind of wideband signals and the specifications of nonlinearity, how these kind of signals get impacted by the nonlinearity. Thank you.